Welcome back. In the last lecture, our discussion was mainly on the ideal gas mixtures and the properties of ideal gas upon mixing, and we summarized that for ideal gas mixtures the delta U of ideal gas is going to be 0 upon mixing. Similarly, delta V has to be 0, delta H has to be 0. However, the entropy is change in the entropy is not 0, and subsequently we derive the relation that delta S of ideal gas is nothing but an R summation yi ln yi with a negative sign, okay, because it has to increase, and this is going to be negative, and hence you have positive delta S here. Now, considering this to be positive, the rest of the things will be also non-zero. Delta G and delta A are the free energies here. Now, I would like to take it forward. Now, we would like to get an expression of chemical potential of a component in an ideal gas mixture. Okay. So, how do you do that? So, let us start with the basic definition. So, I am going to take delta of delta G I G mix. So, I am taking a partial derivative of delta G with respect to N I, okay, and this is nothing but del by del N I, and by definition delta G mix we know is G of I G, and since it is a mixture, let us assume that it is more than one component, right, minus summation N I, and this would be your mu I. This is ideal gas, and this is at temperature T P, and this is for the pure I, right. So, let me use a different symbol here for this. So, this is going to be something like this, right. Okay, so what we are doing here is we are taking the partial derivative of delta G I G mix, which is nothing but the Gibbs free energy of the ideal gas mixture minus that contribution from the pure component, that is for N I mu I. Mu I is nothing but a molar free energy of the pure component here, okay, and that is what is written here. Mu is a function of T P pure I. Okay. So, if you take the derivative here, what you are going to get is the following: del G I G by del N I at temperature T P and J not equal to I, okay, and minus mu I of I G at T P, and then it is a pure, right, correct. So, now you have this expression, and this one is going to be nothing but mu of I, because it is a partial the derivative of the free energy with respect to N I. So, this is a mu of I of ideal gas at T P and the compositions or the mole fraction. So, I can also write like this y I this minus of course mu I I G T P pure, right. So, this is your del by del N I, right, delta G I G mix. Okay, but you have already calculated delta G mix, right, that is your this term. So, I am going to now put this on the left hand side and obtain a separate relation here. So, I am going to use this as this is nothing but del by del Ni nRT summation yi and y, right. So, if you do this, so right hand side is very clear, it is a change in the chemical potential with respect to the pure component, change in the chemical potential of a component I with respect to its pure form, right, at the given temperature and pressure. That is the right hand side, clearly it tells you. Now, let me work on the left hand side. Now, this is written in terms of mole fraction. I can rewrite this thing in moles, so that I can derive it, take the differential better or easier. Okay, so let us look at it here. This is equal to RT is constant, it comes out del by del Ni. So, and this is summation, n is again a constant here, but then yi is nothing but Ni by n. Okay, so this becomes summation, let us say n, let us say I by n ln Ni, right, n, and of course n here comes out, which can be cancelled here. So, this is the expression I have, or this is RT d del Ni summation, and let us say since I want to differentiate with I am going to change this I to j, so that it becomes generic here. This is going to be ln n I minus ln n, right. So, this is the expression we have. So, if you take the derivative here, I can come up with the expression now. This is going to be ln Ni plus 1 minus ln n minus summation nj by n, okay, which is nothing but 1 will cancel out. So, what you are going to get is RT ln Ni by n. Okay. So, this is something which you can do easily, because there is a summation part here. So, if you take the summation this side, then this is going to be summation nj ln n, which is nothing but log ln. Okay. And so, this comes from the first term. This is when you take the second, if you take that by parts, then this comes from the first term and this comes from the second term, and this again if you take it, this comes from the second, and this is the third term here. So, basically what you are doing is you are trying to expand this in this way, summation n j ln n. So, this is j okay, minus summation n j ln n. Note that n is nothing but also summation n j. Now, what you are doing is you are taking the derivative here. So, this first term gives you this 2, second term is going to give us this 2 part. Okay. So, that is what these expressions comes out, and essentially what you get is that this is nothing but RT ln yi. Okay. So, what you have derived is the following, that the change in the chemical potential of a component I in a mixture with respect to the pure component is nothing but RT ln yi. So, that is what you have derived. So, therefore, mu I Ig temperature pressure yi minus mu I Ig TPO I, that is the temperature, pressure and pure I. This would be now RT ln yi. Okay. So, this is your basically the expression which you have developed. Okay. Now, let us look at let us recall what we have learned for the case of the pure fluid. Okay. And so, if you recall that we have written earlier that dg in the, for for the molar case is minus SD plus VdP. This is our, of course, the thermodynamic expression for gas free energy, and dG is equal to d mu, this for the case of the pure fluid, right. So, I can write that in the following for a constant temperature, the d mu is integral of VdP at constant temperature, or I can write this as d mu is equal to VdP at constant temperature, and then if I integrate this, okay, then I am going to write like this, and this will be your mu minus mu 0, and for the case of ideal gas I can write this V as RT by P for ideal gas, and thus I can get this expression as RT ln P by P0, right. This we have written earlier also, right. So, for the case of a pure fluid and for ideal gas, I can write this expression that the chemical potential difference or chemical potential of the pure component with respect to a reference value is nothing but RT ln P by P0. So, here mu here is nothing but Tp pure I, right, and mu 0 is some T some P0 of the same component I, right. So, this is what we have the relation. Now, what I am going to do is I am going to use this expression and this expression, these two expression, and essentially I will combine it. So, instead of just taking a pure I as a reference, I will now take the difference of ideal gas mixtures with respect to a reference state at P0. So, we will just like to see what we are going to get there. Mu I Ig Tp, this is something which can remain in the same. Okay, so, it is like mu I Tp summation by I. So, we can say here combining star and star star. Okay, so, I am not naming or I am not numbering the equation here at this point. So, I am going to use this only the reference as this. Okay, and then I am replacing this mu I ij by this expression, which is RT ln P by P0 plus mu 0. So, because this expression for the ideal gas, so this is also ideal gas, right. So, this is for ideal gas, okay, that is what you are considering here. So, I am going to write this as Tp0 pure I, okay, and this has to be equal to RT ln Yi. So, you need to rearrange now. Okay, so, let us look at how to do that. Again, I am going to use now, make sure that this part is something which can go here. Okay, I will use this as to make sure that we are using the same nomenclature. I am going to say that this is again ideal gas, this is again ideal gas. So, this has to be, let us say, ideal gas, but it is at the P0 as a reference, and this, if you put it here minus of this, so this would be this plus this. So, with this we have the expression mu Ij Tp mu I minus mu Ig Tp0 pure I, okay, but now we have this RT ln P Yi times P divided by P0, okay. So, that is an expression we have, okay. Now, this tells you that the chemical potential of component I here in the mixture with reference to the chemical potential of the pure component at a specific pressure P0, reference pressure, that will be equal to RT ln YIP, okay, which is nothing but a partial pressure divided by the reference pressure. Okay, that is what is basically is telling you this expression. Now, this also suggests that as P goes to 0, that means lower pressure, or Yi goes to 0, that is low concentration. So, low pressure, and this is at low concentration. Okay. So, if the above equation suggests that as P tends to 0 or Yi tends to 0, mu diverges. Okay. But this is the case for ideal gas. So, essentially this equation poses a problem numerically because it will diverge and hence you cannot use it effectively. So, what we would do the same thing as we have done that for the case of the pure system, pure fluid. We will introduce a variable which we have done that past, is called fugacity. So, how are we going to define here? Let me just write it down. So, just as we have done previously for pure component, we will define. So, we are going to define here RT ln Fi by F0, this would be your mu I Tpy, right, chemical potential Tpy minus mu I 0 Tp 0 pure I. Okay. So, this is a generic definition. So, now at this point when I am writing this, I am not saying that this is an ideal gas. Okay. This is to define that the chemical potential difference with reference to reference value is defined as RT ln Fi F0. Okay. Now, here F0 and P0 are related. So, once you fix this P0, basically you are fixing F0. So, usually F0 is 1 bar, at P0 is 1 bar. So, once you say that 1 bar, basically you are saying P0 is also 1 bar. Okay. So, in that case you can simply write this as RT ln Fi is nothing but mu I Tp y minus mu I 0 Tp 0 pure I. Okay. Now, if you want to get rid of this reference, essentially you would also need another condition. So, this would imply also that for another, let us say, pressure, keeping the temperature fixed, you can write this as ln F2 by F1. Let me write it again. So, this is let us say component, we are still talking about component 1 or some I. So, this could be I, this is I, but this is let us say 1, this is 2, and what we are talking about is basically T P 1 minus mu I Tp 2. Okay. So, this is another way to say that if you want to get rid of that. So, essentially you are looking at, you are changing the pressure and you are finding the difference between these relations. Okay. Okay. So, this is just a bit of understanding of the fugacity in this relation, but let us consider a specific case, right, about this part. Okay. So, if you consider this and essentially now consider this for, let us say, compare this one with the definition of the fugacity. So, you use this here and now you compare with the fugacity relation, then the following easily we can derive here. So, if you look at this, this is the same term, but the right hand side, okay, will be your RT ln Yp by P0, that is what written earlier, right, for the ideal gas. So, if you just compare this and apply this expression to ideal gas, mixture, the definition here, then you can show that Fi by F0. So, because it is going to be RT ln F0, this is nothing but RT ln Yi P by P0, right. So, this is what you can clearly say. If you use this expression and compare this with this expression, then essentially you are saying that this right hand side is equal to this, okay, which essentially leads to this expression. Now, this tells you that Fi by F0 is nothing but Yi P by P0. Now, this, though we are saying that is ideal gas mixture, we are applying it to ideal gas mixture, but this particular definition which we have written here does not impose any condition of the phase that is a gas or liquid. So, you can directly consider, also you extend it to the liquid phase as well. So, though I am writing here the mole fraction as a Y, which is usually considered for the gas phase, but this could be a liquid phase also, okay. But of course, we will be mostly using for the gas phase here. So, let us look at it here. So, if you consider this, since F0 and P0 are connected, I can simply write Fi, and this is now for the ideal gas, is nothing but Yip, and Yip is nothing but Pi, okay. So, therefore, Fi of ideal gas, fugacity of a component I in the ideal gas mixture is nothing but the partial pressure, okay. Okay. So, what about the real fluids or real gas? So, certainly real gas will not be equal to Yip, right, and only at specific conditions when the fluid behaves like an ideal gas, you will have Fi real fluid behaving like an ideal gas, then it will have the Fi value to be the partial pressure. So, in order to define the deviation, or in order to observe the deviation from the ideal gas, we can define a very convenient parameter which we call it a fugacity coefficient. Okay. So, it is convenient to define fugacity coefficient because this can identify the deviation from ideal gas. So, ideal gas, so what we can use is we can use this ratio of this Fiig and Pi. So, we can say that Fi by Pi or Fi by Yip. So, this ratio will be called as a fugacity coefficient. So, naturally for the case of ideal gas, this is 1, but otherwise it is not, and this will happen only when the pressure approaches to 0. So, that means basically all the phi in general will approach towards 1 as P approach towards 0, okay, right. Okay, so, that is something which we wanted to discuss at this point, where we started with basically the relations of the chemical potentials with the mole fractions in the binary in ideal gas mixtures, and we started from the derivative of delta G ideal gas mixture, okay, and then we have derived this expression, okay, and then we said, well, the problem comes in when we use this pressure and see that the pressure itself, when it goes to 0, this equation diverges. Then we recall that we have done this exercise in the pure phase, where we have tried to use fugacity as a mean to avoid this kind of divergence of the chemical potentials at a very low pressure. So, we have used that fugacity here as well. Now, we use that expression and connected the fugacity in the gas phase mixtures to the mole fractions and the pressure, and particularly for ideal gas, the fugacity of a component I is nothing but the partial pressure. So, for that, in order to find out the deviation from the ideal gas, we defined a term which we call it fugacity coefficient. So, something which is straightforward at this point. Now the question is, how do we find out this fugacity coefficient when you have volumetric data or equation of state available. So, these are the two specific questions which we need to address. Okay. So, let me just work on this. So, the question is now, how do we relate phi I, right? And if we are talking about phi I, you are also talking about or mu I f I, okay, in terms of measurable quantities. So, this is the basically the key question in at this point, and once you are able to derive this and understand it, then essentially we can make use of whether the experimental data is available or whether the equation states are known. Using those informations, we should be able to find out phi I. We will be also talking about the relevance of phi I when we try to address the questions of the phase equilibria. Okay, and subsequently we also understand how do we relate this deviation from the ideal gas mixtures in terms of other properties also. So, I think we are almost there to understand completely of the gas phase mixtures, and subsequently we will take a liquid mixtures, but this particular question of how do we relate phi I in terms of measurable quantities I will describe in length in the next lecture. Okay, so now I will close it. I will take it up again. So I will see you in the next time.